Hello everyone, today we solve a very interesting question. This question is asked in GATE exam 2024. This question is from ordinary differential equation. Let me write the equation. What is given? Y dash equal to e to the power minus y square plus 1. What can you say about the solution of this equation? And the initial data is given y of 0 equal to 0. Whether the solution exists or not, whether the solution unique. First option is saying that it has unique solution, and the second option is showing that the solution is bounded on the maximal interval of existence. First of all, let us check the option 2, whether it is true or false. Okay, from the given question that y dash equal to e to the power minus y square plus 1, this implies that y dash is greater than equal to 1, because this quantity e to the power minus x square is a non-negative quantity. If we remove this quantity, then y dash will be greater than equal to 1. Means it is showing geometrically, it is showing that the slope of the solution is always greater than equal to 1. Okay, so our intuition shows that the solution should goes to infinity, means limit of y when x tends to infinity, it should goes to infinity, because the it is a strictly increasing function. Y is a strictly increasing because y dash is greater than equal to 1, which is greater than 0. Okay, strictly increasing function, and the slope is also greater than equal to 1. Means geometrically, if we draw the graph of a function y equal to x, its slope is 1. Okay, y dash equal to 1. This function, when x goes to infinity, y goes to infinity, now this function goes to infinity, then our solution has slope greater than equal to 1, so it should lie above of this graph, so it also goes to infinity. So intuition is showing that our solution should goes to infinity. Let us verify it. Okay, this implies that if we integrate on both sides, we will get y of x minus y of 0 greater than equal to x, or y of 0 equal to 0. Okay, so it gives y of x greater than equal to x. But till now we do not know what is the maximal interval of the existence of the solution. So this is one estimate. Second, we also can got that y dash equal to e to the power minus y square plus 1, means our target is so that the solution exists on R, whole R. Okay, this is our target. Okay, and by using this also we can show that our solution goes to infinity also. Okay, from this we can also derive that 1 plus 1, because the maximum value of this function is 1, because it is a decreasing function. It is a clearly it is a non-negative function, but its graph is e to the minus. If you draw the graph of this function, it will look like this. Highest value it when y equal to 0, it is 1. Okay, highest value is 1 of the e to the power minus y square. Okay, so this is bounded by 2. Okay, y dash is bounded by 2, means if we integrate on both sides, we will get y of x minus y of 0 less than equal to 2, y of 0 equal to 0, y of 2 times x. Okay, if we integrate on both sides, y of x less than equal to 2x. Okay, let me write it, equation 2, and it is 1. From 1 and 2, from 1 and 2, we get what? We have 2 what do we have? X less than equal to y of x less than equal to 2x, means at any point the solution is bounded by these two linear functions, means the solution does not blow up at finite x, means it cannot be infinite at finite times, because if it is infinite, this implies it is infinite, but it is always a finite quantity. Okay, means y of x exists on R, means y maximal interval of existence, maximal interval of existence is whole R. okay, it covers the whole real line, okay. And these two things implies x greater than equal to I of x. Now if we take the limit on both sides, then it gives limit x tends to infinity y of x equal to infinite. So our solution cannot be bounded, means our solution is a unbounded solution. So the option 2 is false. Option 2 is showing that this every solution of this initial value problem is bounded on the maximum interval of existence, but we have shown that the maximum interval of existence is r, and on r it is unbounded, it goes to infinity when x goes to infinity, okay. So option 2 is false, okay. And to check the option 1 is saying that it has unique solution, okay. To show the uniqueness of the solution, we will apply mainly Picard-Lindelöf theorem. Picard-Lindelöf theorem or Cauchy-Lipschitz theorem, it is also sometimes called, okay. It shows that y dash equal to f of xy, if this is the form of the equation, then if f is continuous with respect to both x and y, plus f is Lipschitz with respect to y, then it has unique solution, okay. So also we have shown that the solution exists on the whole, if the solution exists, it also covers the whole R, okay, because it does not blow up on the finite x, okay. So clearly here in our question it is that y dash equal to e to the power minus y square plus 1, okay. It is independent of x, so it is continuous with respect to x. Also e to the power minus y square is also continuous with respect to y. So this function is continuous with respect to both x and with respect to both y. So we only need to check the whether this function is Lipschitz continuous with respect to y or not, okay. To show the Lipschitz continuity, if we are able to show that your f of xy is what? F of xy is e to the power minus y square plus 1. If to show the Lipschitz continuity, if we are able to show that derivative of f, partial derivative of f with respect to y is bounded, this implies bounded means it's bounded by some constant k. This implies that f is Lipschitz with respect to y. Bounded derivative means the function is Lipschitz with respect to that variable, okay. So our target is so that derivative of f with respect to y is bounded, this one, okay. Let me calculate the del f by del y, okay. Del f by del y is what? It gives minus 2y e to the power minus y square, okay. If we take the modulus, it gives what? It gives 2y e to the power minus y square, okay. Let me calculate the limit of this function. Limit y tends to infinity, 2 of y e to the power minus y square is equal to limit y tends to infinity 2 of y by e to the power y square. It is algebraic growth, polynomial growth, okay, polynomial, but it is exponential. So if we apply the it is also infinity by infinity form, okay. If we apply the what? If we apply LH rule, then it gives what? A limit y tends to infinity 2y times e to the power y square. So if we put y equal to infinity, it gives 0, okay. So this limit goes to 0. So if we apply the limit at infinity, what is the definition? It shows that for a given epsilon greater than 0, there exists a capital R greater than 0 such that y 2y minus e to 2y times e to the power minus y square minus 0 mod less than epsilon for all y mod less than equal to r, okay. This is the definition of the limit at infinity. Okay, so we are getting that our del f by del y mod less than epsilon for all y greater than equal to r, y mod greater than equal to r. Okay, this is, but we do not know about what happens when, what happens in the interval minus y to y, but we know if outside the interval it is bounded by this epsilon. Okay, but we do not know on this interval, but we know that our del f by del y mod is equal to 2y e to the power minus y square. It is a continuous function, continuous one. Okay, continuous. So on this it is a compact interval, and it is a continuous function. Wait, I have missed something. It is not minus y to y, it is minus r to plus r. Okay, on this interval, on the outside of this interval we know it is bounded by epsilon. Okay, and the inside of the interval we do not know, but we know that inside of this interval our function is continuous and it is a compact interval, it is a compact. We know that continuous function attains its maximum value on the compact interval. So del f by del y is bounded by some constant k1 on minus r to r, because this is a compact interval. Okay, so these two things, this is a double star, okay, and this is star. Okay, star and double star implies from star and double star we have what? We have del f by del y mod less than equal to maximum of epsilon comma k1. Okay, this implies that del f by del y mod is bounded. This implies that f is ellipsis continuous with respect to the dependent variable y. Okay, so by the Cauchy-Lipschitz theorem or Picard-Lindelof theorem, the problem has unique solution on R. Okay, so option 1 is true and option 2 is false. So the correct option is option B. I hope that you all understood it very well. Thank you all.